So I think we're ready to go for this morning's talks. Nigel will be continuing on with transitions to turbulence, violent fronts passing through us, puffs, and other things. Take it away.
Okay, good morning. So today we're going to start off by talking about linear stability analysis very briefly. I think you all know a little bit what linear stability analysis is, so I'm not going to work through any detailed calculations of it, but I have left in my notes that I will put online today some details of how one does such a calculation in the case of convection. But what I'm going to start off with is talking about some results on linear stability analysis and what they tell us about the transition to turbulence, if anything. Then I'm going to get into the meat of today's lecture. We're going to talk about experiments, very detailed and sensitive experiments that were done about 10 years or so ago, continue to this day on puff dynamics. We'll talk about the theory that we developed for this. And I'm not going to give a full comprehensive survey of all the different theoretical approaches to this problem. There are many. And I will mention in the last lecture just some of the things that I had to omit for reasons of time, rather than not to imply that they're any worse or anything than what I'm going to be talking about. But these are the topics I'm going to talk about. I will take some Blackboard lecturing to explain to you about rhythm scaling, which we will use next time as well, and some calculations on predator-prey dynamics. And then we'll talk about how we see that the actual transition is in the universality class of directed percolation. And then I'll talk about at the end the experimental verification for that. And next time we will talk about puff interactions and then how puffs spread and turn into slugs. All right, so let's start off with the first topic, which will be, I will use the Blackboard. So let me get some chalk that works. All right, so this is, all right, so this is in my notes, it's section 2.2. So the goal of what we're talking about today is to understand the transition to turbulence, not as a function of how turbulence might spread and contaminate a region and cause it to become turbulent, but now looking at a whole bulk system and asking what happens as we raise, say, the Reynolds number or the Rayleigh number or some other thing. So what we're looking at is how does turbulence occur globally as we vary an external parameter. That parameter might be the Reynolds number, but it could be Rayleigh number, maybe other things as well. Okay, so that's the question. So answer number one is look at the steady states of the Navier-Stokes equations, which correspond to laminar flow. And then compute the linear stability around that state. And we will in general be thinking about states that are easy to do linear stability around. So for example, for pipe flow, that would be the Hagen-Poiseuille flow, which I will write down in a minute or two. And then see when it goes unstable. Of course, when you do that, you don't know what it's going to go unstable to. In the case that I worked through in detail in my lecture notes, just for those of you who perhaps never seen this before, I do this for a Rayleigh-Bernard convection, where you're looking at a fluid heated from below, and heat is conducted by diffusion through the flow. And as you increase the distance between the plates, or you increase the, well, that would be one way to do it, for example, the temperature difference, then what happens is you make a transition to a non-conducting state. And that non-conducting state is not turbulent. It's a state where actually you get a pattern formation, and so there's a sequence of patterns that intervene between the laminar state and the turbulent state. And so then it becomes very complicated to do this sort of analysis. But anyway, let me just tell you the results of what happens when you do that. So let's just say that in the case of a turbulent convection, which will be in my lecture notes that I'll upload this afternoon, there is a super critical bifurcation from the uniform conducting state this is to roll patterns and not turbulence. And there is a sequence pattern forming instabilities before you get to turbulence. So that's bad, and the reason it's bad is that once I've got a roll state and I want to look at the stability of that, well, what I now have to do is I have to do linear stability analysis, perturbation theory, about a periodic state. And then that might go unstable to some more complicated state, and so on and so forth. And it's a losing game. Now, so that's not good. So let's talk about what happens in pipe flow, which is what I'm going to be mainly interested in for today's talk. So the setup for pipe flow is I have a pipe like so. We'll call this the x-axis. Here is the radius of the pipe. Let's call it A, and I've got a pressure gradient which will be uniform. Let's just write it down as dP by dx, which is negative because I've got a high pressure up here, a low pressure over there. And then if you just solve the Navier-Stokes equations, you plug this geometry in. The nice thing is that because of the advective instability, the advective term, I should say, the separation of the directions means that you get a linear equation. It's trivial to solve it. And so what you get is the Hagen-Poiseuille flow. Hagen-Poiseuille says that V is basically 1 minus R squared over A squared. comes from characteristic velocity in the x direction, and that is connected to the for you see over a squared like that. So that's the Hagen-Poiseuille flow. And when you do linear stability analysis for this, well, we don't know how to do it in detail for all Reynolds numbers, but what people believe is this. What we know is we can show that it's stable up to about 10 to the 7. This is a numerical work. And there's a belief that we can't, to my knowledge, there's no proof as of now that smooth pipes are linearly stable for all Reynolds numbers. Okay, so that's the first thing. Now, the next thing is you might say, well, do we really believe that? What, because are pipes really smooth? And of course they're not. So here's a recent paper. So this is a paper from 2021 by Hall and Zakir in JFM. And what they show, and I'll put this in the library for you, in fact, it may already be there. I don't know if it's been put in yet. If you have a roughness of scale epsilon, so you can imagine putting those sand grains on the side of the pipe, just like I showed you yesterday with Nicorad. That gives you, it becomes unstable, scales like C epsilon to -3/2, log of epsilon to -3/4, where the constant C is something like 30 or something like that. So there's this intuition then that as I put some roughness on, there is a critical Reynolds number that comes down from infinity with the scaling that is shown over here. And if I get time in tomorrow's lecture, I will talk about the Nicorazzi problem and the scaling there, the critical scaling that I worked out nearly 20 years ago. And in that, we assume that there is a singularity in this roughness scale, and this is shown explicitly over here.
You know, whenever I see log corrections, it's interesting to me. Is there some intuition for that?
There may well be, but I don't have a hand-waving argument for it. But yes, logarithms are, the knee-jerk reaction is when you see a logarithm, my heart is raised a little bit, yes. Yeah. All right, so let's now talk about plane correct flow. So for those of you who may not be familiar with plane correct flow, so the idea is I have two plates like so. So there they are, and then this top plate is sliding to the left, the right. The bottom plate is sliding to the left like so. So if I asked you to guess what the velocity profile looks like using the usual non-slip boundary conditions, your picture for the velocity profile would look something like that. There'd be a linear change in the mean velocity, and this can be shown to be always linearly stable. And that was worked out by Romanov 50 years ago. And so that's true. However, experiment disagrees with theory. Experiment says no, there is a critical Reynolds number, and it's about 350 or something like that. Okay, so that's plane correct flow. Now let's talk about another geometry. This one is plane Poiseuille flow. So plane Poisson flow is basically a pipe version of a planar version of a pipe. So you have walls like this. So this is meant to be going off in the third direction. I've got these parallel pipes. But now what I have is a pressure-driven flow. So this is pressure-driven. And so if you work out the velocity profile, it's exactly what we had before, the Hagen-Poisson flow, a parabolic profile like that, but then extended into the board. And so that's plane Poisson flow. And this was the subject of Heisenberg's PhD thesis. And Heisenberg did his PhD with Sommerfeld. And Sommerfeld was one of the first people with OR to make this whole program of linear stability analysis. And so they derived what's known as the Orr-Sommerfeld equation. And when you try to do these linear stability analyses, the equations that you get are quite complicated and very hard to analyze. And Heisenberg's PhD thesis was take the Orr-Sommerfeld equation for this flow geometry and try to see if there's a critical Reynolds number. And what Heisenberg discovered was yes, there's a critical Reynolds number, and it's about it's basically UC H over nu, where this plate spacing is 2H, and so this is about 5772, I believe, and the way that Heisenberg proved that is really quite remarkable. Lots of mathematical ingenuity going into solving this problem. It is, however, completely wrong. H is not Planck's constant, no. So H is this H here. Okay. However, it disagrees with experiment, and that's the ultimate arbiter. So experiment is that there is a critical Reynolds number, but that number is about 1500, much lower than what Heisenberg predicted. So what is the resolution of all of this? We seem to have done a lot of hard work. Well, Heisenberg did, and what was the end result of that? Well, the conclusion is that linear stability analysis is not what's going on here. But actually, what must be happening is that there are finite amplitude instabilities. Those are excited by whatever is around in the environment, and the actual transition is a transition that occurs through a finite amplitude instability, even if mathematically the transition could be a supercritical one. So the conclusion is that there's finite amplitude instabilities, and so basically that means that linear stability analysis is irrelevant, at least linear stability analysis about the uniform trivial states. And do we know anything about these finite amplitude instabilities? Well, Björn Hoff in 2003 did an experiment in pipe flow where you can show that the finite amplitude instability varies with Reynolds number with a power law that Björn, when I last asked him about this, he declined to say whether it is really 1, but it's roughly 1 anyway. So he's a very good and cautious experimentalist. And so there is evidence that the critical threshold that you need gets smaller and smaller as you increase the Reynolds number. So eventually you get to high enough Reynolds number where anything that's going on in the environment will cause the system to go into a different state. And so what that means is that we need a systematic study of subcritical transitions. Subcritical because you make a jump, and so it's not the same as you would get if you had a supercritical transition. All right, so that's where I want to leave the blackboard for the moment. So there's a lot more stuff in my notes that some of you might find interesting, and I will return to the blackboard in a little bit. But for now, I'm going to go back to the lecture on PowerPoint. And I brought with me, well, if I use a laser pointer, will the people on Zoom be able to see it? No, they won't. They will? Okay, really? Well, then why?
You're watching from the camera.
Uh-huh.
You can see everything.
Oh, okay, but really they're seeing this thing here. Well, then maybe I'll just use this. I hate to be stuck in one place. Let me move this thing out of the way. All right, so here is the notional phase diagram of turbulence, and the numbers here are appropriate for pipe. As you can see, there's the laminar flow, which is steady and predictable. At high Reynolds numbers, you have this fluctuating, unpredictable turbulence, and here is the laminar turbulence transition, and you can see these nice fronts between the turbulence and laminar regions, as we talked about yesterday. For pipe flow, this critical Reynolds number is about 2000. There are universal phenomena at the transition to turbulence, but as you'll remember from phase transitions, the critical temperature is not universal, and the same thing is true here. The critical Reynolds number is not universal. All right, so the thing I'm going to do that is different from what most theorists would like to do is this. I insist that every picture I show here has a flow. It has it's an open system. Fluid is coming in from the left, going out at the right, and it's turbulent on the right, and it's not turbulent on the left. So we don't have periodic boundary conditions. Why is that? Well, because as I've just explained, turbulence is generated by instabilities. It could be either linear and long wavelength, if you have some supercritical bifurcation, or they can be nonlinear and spatially localized, as we have concluded from everything that I showed you on the blackboard, reported to you about the instability. So you have localized, spatially localized, nonlinear finite amplitude instabilities. And symmetry is the enemy of instability. Turbulence is fundamentally about instabilities. So if you're a theorist and your gut reaction to anything is 3D homogeneous isotropic turbulence, periodic boundary conditions, you've thrown out the baby with the bathwater. So if we really want to do this properly, we have to deal with this boundary conditions. The other thing I want to mention is, why is this problem so hard? The problem is hard because turbulence interacts with mean flow, and turbulence itself can generate emergent mean flows. And Brad Marston, Steve Tobias, and perhaps others here, that's one of the things that they've been focusing on in some of their recent work, as well as others, Grisha Falkovich. And so this is what makes the problem so difficult. Now, as you know, at high Reynolds numbers, we have fully developed turbulence. So we have an energy cascade, a non-equilibrium steady state where energy is pumped in, transfers step by step, scale by scale, and then eventually is dissipated at the Kolmogorov scale down here. And I'm sure you've heard about this, but just in case you haven't, the energy dissipation rate is given by this formula, and it's non-zero as nu tends to zero, as the viscosity goes to zero. Okay, so this is a surprise. How can you have dissipation when there's no viscosity? And that's the dissipative anomaly. It was the first anomaly discovered in physics, and it's related to anomalies in quantum field theory and other things. Well, wouldn't it be great if this thing transferred? Okay, transitional pipe flow. I'm going to talk a lot about this phase diagram, okay? But it's a complicated phase diagram, and as you can see, you get flow configurations. What's shown here is the turbulent intensity from computer simulations, and this flow diagram is quite complicated, and that's the subject of today and tomorrow's lecture. And then in the middle here is where you've got turbulence, but now it's interacting with the mean flows. This is the regime I showed you yesterday in the Nikoradze plot, where you can see this scaling with Reynolds to -1/4 and so on. So that's well, I'm not going to say very much about this. Now, I do want to say something about the energy cascade, because this is going to come into what we talk about later. So you all know that Commonwealth and Richardson's idea was that energy transfers from scale to scale through swirly whirly eddies that spin off smaller and smaller swirly eddies, and they do that in a Hamiltonian way. So naively, people say, well, that means that viscosity doesn't enter into the equations. Now, I want to go through the Kolmogorov scaling argument, because I'm sure I know you've heard it, you must have done, but I want to make sure that you've heard it from me, because I want to say it in a slightly different way than other people do, and you'll see why later. So what is important about this? Well, this is the kinetic energy per unit wave number range K, and it's got to depend on wave number, the energy input rate, which in steady state is the energy dissipation rate, the kinematic viscosity, and the system size. Out of these quantities, you can make the Kolmogorov scale u cubed over epsilon to the 1/4. And so I can then write down, without loss of generality, that E of K must be nu squared over eta, some function of K times eta, which is dimensionless, some function of K times L, which is dimensionless. Dimensional analysis tells you one and only one thing, that a dimensionless variable can only be a function of other dimensionless variables. Okay, so that's all that dimensional analysis tells you, nothing more, nothing less. Next thing you do is you make an assumption. I'm going to take the Reynolds number goes to infinity limit in two different ways. One of those ways is I'm going to keep K constant. I'm going to send L to infinity, so KL goes to infinity. So what you're going to say is, well, that's fine. I just replace KL by infinity over here. And now what I've done is I've taken this function of two variables and turned it into a function of one variable. That's why you do dimensional analysis. But in physics, we teach it badly. Often people think that that is dimensional analysis, but of course it's an assumption. You're making an assumption about asymptotics. And in the Russian literature, Zeldovich and Barenblatt called this complete similarity. Let's just ride with it for a moment. So now you set this equal to infinity. Now I want to look at this variable here. And now what I'm going to do is I'm going to take the limit of infinite Reynolds number by sending nu to 0. I send nu to 0, eta is going to 0. I keep K fixed. So I said this equal to 0, because I'm going to, but it's not going to work quite as simple as that, because you can see that nu is inside this function, nu is outside here, and nu is inside eta K. So as I take the nu goes to 0 limit, this thing in front is either going to go to 0 or infinity, unless the nu dependence inside here cancels out with it. And the only way that can happen is f is a power law function. What power law? The power law is determined by making the nu dependence vanish. I'm going to show you another example of this on the blackboard later on. So we're going to assume that K eta goes to 0, and then what happens is you get a constant, which I've inaccurately written down as f0 in infinity, and then it turns out you get epsilon to the 2/3, K to the -5/3. So this thing over here is what is known as Kolmogorov's first similarity hypothesis. There's a second assumption that goes into this. And so that's how you get the K to the 5/3 law, and you get the familiar K41 spectrum. So the only problem with this is it's wrong. It's wrong because this assumption of complete similarity up here is not correct. And what we believe is that there's large scale intermittency. That means that this limit isn't isn't a smooth limit and isn't defined. And so we call that incomplete similarity. And what happens is as you take KL to infinity, this function actually scales as another function just of the first argument times KL to the power eta. Eta here is not the Kolmogorov scale. Eta here is an anomalous dimension, an anomalous scaling exponent known as the intermittency exponent. Okay, if I get time at the end of these lectures, I will show you how from Nikaradz's data taken in 1933, 8 years before Kolmogorov did this argument, the mean field argument, 8 years before that, just taking Nikaradz's data, you can already deduce, using techniques from the normalization group, this intermittency exponent, this anomalous dimension of turbulence. Okay, so now on to puffs. So here is Reynolds. Reynolds' assistant, in fact, are standing on this apparatus. And what you're doing is injecting fluid into this pipe through this nozzle here, trying to get the flow domain as smooth as possible. At low Reynolds numbers, it's smooth, regular, and laminar. At high Reynolds numbers, you get turbulence. And in intermediate Reynolds numbers, you get what he called flashes of turbulence, which today we call puffs. And I will put, well, there may already be there, Reynolds' original paper in the papers that I'm sending to you. So the most naive question that you can ask is, I've got this sequence of snapshots as I increase the Reynolds number. The most naive question you can ask is, how much turbulence is there in the pipe? So you want to basically look at how long these turbulent regions are, what fraction of the pipe is occupied by them, and what fraction is occupied by lambda. And if you do the experiment, well, these are data not on this geometry, but on a different geometry, which I'll talk about. The turbulent fraction goes like this. And that's just experimental data taken by Hoff, I don't know why it's not on there, in 2015. Okay, so again, as I've said, the transition is not spatially uniform. There's rare, sharp bursts of turbulence. Okay, so now we know two things. I've shown you two stylized facts. One is the turbulent fraction as a function of Reynolds number. And you may look at that and you may say, wait, Nigel likes phase transitions. So maybe he's thinking that this is a phase transition. So you're right. And this looks like say how the order parameter varies as you go through a second order phase transition. The other thing you'll see is that if I look at the energy spectrum, when I'm measuring this, what I'm really measuring is, of course, an average. So when I'm measuring the energy spectrum, what I'm actually measuring is the velocity autocorrelation function. So I'm measuring the correlation function of velocity fluctuations in the inertial range, and that goes like a power law. And so we all know, again, the signature of continuous phase transitions is that you get power law fluctuations as you go through the transition. And I didn't mention this, but it was implicit on the earlier slides. The range that you have, the inertial range, here is the integral scale. Here is the Kolmogorov scale. As I send nu to 0 or Reynolds number to infinity, that range of scales increases. In 3 dimensions, it goes as Reynolds to the 9/4 power. That's the number of degrees of freedom that are strongly interacting. So
naively fit an exponent to that concept. Does that make sense to you?
This one, which one? This one here?
Left, not left.
I'll show you what the exponent is. In this particular case, it's 0.276. Good guess.
Yeah.
How you can see a quarter from that is impressive. Impressive, because the exponent is Reynolds minus the critical Reynolds number, and you can get any exponent you like if you fiddle around with the critical Reynolds number. So you have to do it very carefully. So any good textbook on statistical mechanics and the normalization group in chapter 7 describes the difficulties in fitting experimental data. Yeah.
Just to clarify, so if you increase the Reynolds number, you calculate the average fraction that's by length that's turbulent between the time of the average of the length.
If you want, actually, it's simply measured. So I'm showing you experimental data, not theory. But yes, yeah. So you're sitting there with a pipe, and you can measure the puffs by pressure sensors. And so you just see how big they are. You can do this in computer simulation. You do this many, many, many times, and that's how you get those data. Okay, so why is this problem so hard? Why are we even having a section on turbulence in the summer school? Why wasn't this solved years ago? So as I've argued, at least suggested, we should think about turbulence in perhaps the language of phase transitions. I'm not the first person to think of this. This was already thought up by Krishnan in the 50s and 60s, my PhD advisor Sam Edwards in the early 1960s, and many others since then. But we have a better understanding of phase transitions today, and we also have better data. So if you want to understand why the turbulence problem is hard, you might ask yourself, well, why is the phase transition problem hard? Okay, so why is it hard? Well, you have an order parameter which is strongly interacting, and the fluctuations in that order parameter are very non-Gaussian, and you have intermittency. And so here are some simulation data. This is the probability distribution of fluctuations. It's not a very good graph here, but it doesn't matter. And you can see there's non-Gaussian, a lot of skewness evident. Now, the main reason theoretically why this is a problem is that there's no usable small parameter. Wait, so why is there no usable small parameter? So you say, well, wait a minute, there's obviously a small parameter in phase transitions. I'm looking at temperature T close to the critical temperature Tc. So I can make a small parameter. There's epsilon over here, T minus Tc over Tc. That is obviously a small parameter. So there's a small parameter in the problem. So why is it hard to solve? I can just do perturbation theory. Well, the problem is this. Here is the Landau free energy that describes the system near the critical point. This is it in its sort of physical units with a length scale here, or inverse length scale squared, and so on. These coupling constants here are naught and u naught. R naught is proportional to T minus Tc. U naught is a number that tells you the strength of the interactions between fluctuations. Now, again, if you look on page 191 of any good textbook on the normalization group, what you will find is that after I've done dimensional analysis on the statistical thermodynamics, the field theory that describes this, all these coupling constants, gamma and R naught, basically go to 1. And the only one you have left is the one here, which I'll call U naught bar. And that is U naught 2, but I'm not. Thank you. Great. So it's not hard to do this. What that means is that in D less than 4, less than 4 dimensions, the coupling constant goes to infinity, not to 0. And so that's why I say there is a small parameter, but it's not a usable one. All right, somebody had a question. I think you did. Did I answer it already?
Sorry.
Did I answer it already?
I'm just curious about what is order parameter you
In the figure there, it would be the magnetization fluctuations in a magnet. So the order parameter is the number of spins pointing up minus the number of spins pointing down if I have an Ising model. And the magnetization is the difference between them. So if I'm at high temperatures, as many spins point up as point down, so the number of spins up minus the number down is equal to 0. As I go below Tc, that number becomes non-zero. That's the phenomenon in an external magnetic field. That's the phenomenon of spontaneous magnetization. So I suddenly find that below the Curie temperature, more spins point up than point down, or more spins point down than point up. And so I have a non-zero remnant magnetization, and that's the phenomenon of spontaneous symmetry breaking. And the real way to describe that is not to say lower the temperature and you find one or the other. What you actually do is you apply an external magnetic field to a magnetic system. That external magnetic field lines the spins up. So now they're partially lined up, but of course, how much they line up depends on the alignment energy with the external magnetic field and fluctuations, thermal fluctuations from temperature, which try to randomize the spins. Now I take that external magnetic field to 0. When I take that external magnetic field to 0, you would say, well, once that field is gone, the spins are going to be completely randomized by thermal fluctuations, as many spins point up as point down. And that's true above the Curie temperature. But below the Curie temperature, even as I take the limit of the external magnetic field going to 0, the spins still stay pointing up in the direction that that external magnetic field is. And so you have a spontaneous magnetization or remnant magnetization below TC. And then there's two probability measures that describe the system. One with spins mostly pointing up, one with the spins mostly pointing down, and they're related by the up-down symmetry of the original Hamiltonian. Does that answer your question?
So these are for magnetic systems, not turbulent.
These data here is a phase transition in an equilibrium magnetic system. Yeah. So, yeah.
And do we have a similar order parameter in turbulence?
I will talk about that. Okay, but
Now you're talking about.
yes. So I know that there's a wide range of backgrounds here. So I gave you a long answer to your question to sort of try to bring you up to speed on some elementary phase transition physics. If I mention anything that is like you missed it, please ask, because there's bound to be several people in the room who have a similar thing. Okay, now let's talk about turbulence, not magnetic phase transitions in equilibrium. In turbulence, you have strong interactions and fluctuations in the velocity derivatives. If I plot probability distributions, it's not of the order parameter, it's of the gradients of the velocity field. And here are some graphs as shown over here. The velocity field itself has Gaussian fluctuations, but the velocity derivatives have very long tails. And you have intermittency, bursts of strong fluctuations, and then weak fluctuations. So very similar to what you have over here. Then there's no usable small parameter. And you might say, of course there's a small parameter. We're taking the Reynolds number to infinity. So 1 over Reynolds number is small. There's my perturbation parameter. Well, no, because look at Navier-Stokes equations and look at the way nu going to 0 comes in. It comes in, first of all, it's a singular perturbation, multiplying the highest derivative in the PDE. And second of all, the ratio of that term to the inertial term goes to infinity, not to 0. And so again, we have no usable small parameter. Okay, now the phase transition problem was solved. Wilson got the Nobel Prize for developing the renormalization group. His renormalization group was based on Kadenov's scaling ideas that connected fluctuations in the Hamiltonian at one scale to those at another. And that explained data collapse that was discovered by Ben Widom. Do you have a question? Yeah. Yes.
Why is this second?
So let me see if I understand your question. You're asking, let me go back to this slide over here. You're asking if I have a differential equation and it has a gradient expansion and some of the coefficients are equal to 0, it doesn't matter, but why does it matter for the second derivative in this one?
Right, so we have also the fourth derivative.
That's right. That's right. So the fourth derivatives don't matter as long as I've got the second derivative there. But if I don't have the second derivative there, so let me put it this way. There's two ways to see this. One is once I have a differential equation and I add a higher order derivative, I've changed the number of boundary conditions. Once I've changed the number of boundary conditions, then I can get all sorts of phenomena, such as, for example, boundary layer formation, which of course you know in fluid mechanics happens a lot. Once I have this and now I add a fourth order term, it does make a difference, but it doesn't make a qualitative change to the type of the solution. So some perturbations are singular perturbations, some are regular perturbations, and I'm not going to have time to go into a whole detailed analysis of this. But this term here, just like the highest derivative in the Schrödinger equation, is h bar squared over 2m del squared psi blah blah blah, right? Quantum mechanics, if I set h bar equal to 0, the Schrödinger equation is just an algebraic equation. So adding that lowest derivative term qualitatively changes the nature of the problem, and that's the whole topic of singular perturbation. So did I answer your question at least without going into too many details? Okay, good. All right, so they both have strong fluctuations, parallel correlations. can we solve turbulence by following the methodology that they used to solve the critical phenomena problem? So the answer to that is, I think you can, and I'll show you about that if we have time. It's not the main topic of today's of our lecture here. And does turbulence exhibit critical phenomena at its outset? And the answer is yes. So let's now talk about the modern era of turbulence experiments. And my favorite paper in this is the paper by Bjorn Hoff in 2008. That paper came 2 years after another paper, but again with Bjorn Hoff as first author and Bruno Eckardt as last author in Nature. And they used similar techniques as this and discovered something very interesting, which I'm going to show you about in a minute. So we're going to talk about the results in the 2008 paper, but when I get to the data, I will make a comment about what happened in the 2006 paper. Okay, so what's the setup here? Well, it's just the same as Reynolds, except there's a difference. The question we ask is different. So the idea here is take a pipe, fill it with fluid, make the pipe have laminar flow, make the pipe be very smooth, make it be very long, control the temperature of the fluid extremely well. Why do you want to do that? Well, the Reynolds number is extremely sensitive to thermal expansion and things like this. So temperature control is the biggest problem here. And then what you do is you inject turbulence over here. The turbulence now goes down the pipe. So here's the turbulence going down the pipe. And as it goes down the pipe, it dies away. Why does it die away? Because you're below the critical point, the critical Reynolds number of turbulence. So you do that again. There's the turbulence fluctuating. And maybe this time it gets to the end of the pipe and comes out the other end. Now, as we know, turbulence causes drag. So when it comes out the other end, if turbulence has survived, by the time you get to the other end, it's going to come out slower. So it'll follow the red trajectory. If, on the other hand, the turbulence died halfway before it got to the end of the pipe, let's say, then the fluid will come out faster and it will follow the yellow trajectory. So the only question we're going to ask is this: did the turbulence get to the end of the pipe? Yes or no? Okay, binary question. And then let's do this, say, 1,000,000 times. And from that, we can work out the probability distribution for whether the turbulence survived as it got to the end of the pipe. Then the next thing I can do is I'm going to vary the Reynolds number by varying the input speed. So I know how fast the fluid is moving through the pipe. And I can vary this distance between where the fluid came in, the disturbance came in that created the turbulence, and when it comes out. So I can do time of flight measurements on turbulence as it goes through there, and I can measure the survival probability of turbulence as a function of Reynolds number and time.
It's a deliberate perturbation.
It's a deliberate perturbation because you set the thing up to be in the laminar state, which is very stable. Okay, I didn't tell you this, but if you're very, very careful, you can make a pipe be laminar all the way up to 100,000 Reynolds number. There's one paper from the 1960s where they reported that. The actual transition to turbulence, meaning the lowest point at which turbulence will occur, is 2038. So it's you can have metastability. All right, so this is what they found. They found that the probability was a memoryless process, a Markov process. It decayed exponentially in time, as I've shown you here, with a lifetime given here. And here are some of the early data. There's better data now. But these are data. This is a log scale. This is time. And these are different Reynolds numbers, as shown over here. So this lifetime here, this mean lifetime that comes into this survival probability, is a function of Reynolds number. And here is what it looks like. And you can see here, this is a logarithmic scale of lifetime as a function of Reynolds number. And you can see that this is a curve that is curving up. The curve that is curving up on a log, semi-log plot means that that function is growing faster than exponential. And there's no end in sight. So in 2006, when Hoff and co-workers started to see these types of curves, they said, wow, turbulence doesn't exist. Because the lifetime, however high in Reynolds number you go, the lifetime seems to be finite, but large, And so that suggests that turbulence doesn't exist. Turbulence is just a metastable state. If I took turbulence, waited, say, the lifetime of the universe, it would come back to lambda again. We don't believe that today, but that was the idea that turbulence doesn't exist. Okay, so that's not true. So that's why I have to tell you about metastable puffs. Now, when you go to a higher Reynolds number, now what happens is something very interesting. That puff, as it wanders down pipe, and there's the puff from numerical simulations, it actually splits into two. The second puff speeds up, runs away from the mother puff, and then eventually becomes independent from it. And then eventually it either decays or it splits as well. And we'll talk about that process a lot tomorrow. So that's a regime which we'll call spatiotemporal intermittency. And you might ask the following question. How long does it take for the first puff to split into two? Well, let's think about that. As you go up in Reynolds number, the thing is going to become more and more turbulent. So you might then say, well, that time scale should go down as the Reynolds number goes up, because it waits a small amount of time for splitting. Splitting is good because it creates more turbulence in the flow. And we know that as you go to larger and larger Reynolds numbers, you're going to end up with a pipe that's full of turbulence. So you would expect that this curve would start off small over here and increase as I go down in Reynolds number. And that's what happens. You look at the mean time between splitting events. Those are the data from Hoff group. This is from a 2011 paper. And again, you can see this upward curvature indicative of the fact that there is a faster than exponential increase in this time. Now, if I take this double log of that, those data fall onto a straight line, and they intersect at this point here, which is the critical Reynolds number. Now you may say, why take a double log? If I take a double log of a function, any function is going to basically look a straight line. But there is a theoretical reason why this is the right thing to do. This is what's actually happening. I'll talk briefly about that in a minute. Now, why do you call this the critical Reynolds number? Well, what that says is that if I wait a long time in a large pipe, and I've got a puff there, I'm above this critical Reynolds number, there's a probability that that puff will have split, and they'll be splitting as well. And so at long times, I will expect to have probabilistically some turbulence still in the pipe, whereas over here, I won't. So the intuition is that if I measure the turbulent fraction in the pipe, it will be 0 over here, and it will be non-zero over here, because there's always a puff that can split, and so there'll still be a long time some turbulence still left in the pipe. And we'll quantify that statement later. Somebody had a question. You first, and then you. Please go ahead. Yes. Actually, it doesn't. We actually know this from computer simulation, and this was work that was really started off by Dwight Barkley and Moxley about the time that these experiments were done, and we could do direct numerical simulations of some of these things. So we know that the puff actually moves slightly slower. So in the moving frame, it actually moves backwards. And in tomorrow's lecture, I'll talk a little bit about that. Okay, but it's a small effect. Okay, you had a quick question? Wait, the region of turbulence gets smaller?
I mean, if they split the region, the puff, then they decrease in size, right?
No, the puffs stay the same size. Oh, so I didn't say this right. The puff splitting, it's not like it gets smaller and smaller, like me repeatedly smashing my laptop, so the pieces get smaller and smaller and smaller. Okay, think of this as a bacterial cell that makes a baby cell, and then the baby cell then grows to be the same size as the mother. Okay, that's an accurate analogy. Did I answer your question? Sure. Question over here. No, it depends on. It doesn't depend on the puff size. The puff. I think you're asking the question: when do bacterial cells split? Is it dominated by how big the cell is, or is it dominated? Is it controlled by a time, a timing clock? Is that what you're asking? So the splitting of the puff is a stochastic event, and the mean time that governs that is a thing that's shown here. And what causes the puff to split is random fluctuations. And so it's not that the puff starts off, grows and grows and grows, and then splits into two, and then those daughters grow and grow and grow and split into two and so on. Is that what you're asking? I'm sorry that I'm not quite understanding the question. Yeah, so that would be one hypothesis, but that's not what happens. What happens is the puff forms, it immediately gets to a certain size that is controlled by the streamwise interactions, which I'll talk about tomorrow. Once it's got that size, it just sits there and wanders off and does its own thing. And then eventually it decides, poof, I'm going to split. And so it splits. And then a new daughter puff starts off here, very quickly grows up to the full speed and full size. And then it wanders on its way and does its own independent thing. So did I answer your question? Correct. Thank you. Yes, great clarifying question. So all I have to do is do that, and then I create a puff. And what happens is as I said, it's a localized nonlinear finite amplitude instability, like a nucleation event. So once it's triggered that, there's a complicated process by which that delta function, if you like, grows and becomes a puff, and the finite size and the finite shape of the puff that you can see in those pictures there is determined by the streamwise interactions. And I will explain those tomorrow. So very good question. Thank you. Okay, so what I've told you is that any time scale you would care about scales super exponentially as e to the Reynolds number. Okay, I will briefly talk about where that comes from later. Okay, now let's talk about the theory for this. In order to talk about the theory for this, I have to remind you, what is the theory for magnetic systems or equilibrium phase transitions? And the reason I want to explain that to you is not just to teach you that, because I think many of you know it, but some of you will not, but also to remind you that there are some questions that we can ask about phase transitions that even today we do not know the answers to. And so we should not expect from transition to turbulence an answer to questions that we can't even answer for the simplest equilibrium textbook examples like magnets and so on. So here's a magnet at the lowest level of description. It has electronic structure. We heard yesterday from Abel's lectures that there's a huge range of scales and so on. So here we're now starting to talk about these range of scales. So we have electronic structure at one level. The electrons move around in a solid. They interact through their spins, their dipole moment, if you like. And if you want to try to understand this, you'll say, well, forget about the electronic structure. I don't care about the band structure. I don't care about any of the other things. Let's just look at the magnetic moments. So I make a model of spins interacting. That model is called the Ising model. I'm sure you've all heard that. And that model might be a Ising model, or it might be a Heisenberg model, meaning the spins can rotate, but it's some sort of model like that. It would be a quantum mechanical model, or it might be a classical model. You might just say, well, forget about quantum mechanics, it's too hard to solve. Let's try to look at a classical model of spins interacting. You can't solve that either unless you're in 2 dimensions. And there's no external magnetic field. And your name is Onsager. If your name is Onsager, you can solve it, okay? Okay, so external magnetic field, can't solve it. Okay, 3D, can't solve it. But in 2D, you can solve it exactly. But that doesn't matter, because what's more important in physics is being able to solve everything to an arbitrary degree of accuracy, rather than being able to solve a few things exactly. So exact solutions we can't solve, it doesn't matter. In general, you say, I can't solve this, say 3D Ising model. So then I write down the Landau theory, the coarse-grained free energy that describes the system as a function of its magnetization near the critical point, and then I use a renormalization group and blah, blah, blah. And I find out all the details about the transition, including all the singularities. So let me show you how that works. I'm going to give you a Blackboard lecture for a few minutes. So the thing I want to talk about now is the stylized facts. The phase transition. The reason I want to talk about this is because the argument I'm going to make is the same argument that Commonwealth made in K41, and it's the same argument that we will make tomorrow at the end of the lecture when I talk about the go back to the nuclearity problem. So here are two stylized facts that were known in critical phenomena for a long time. If I measure the magnetization, which let's say is the number of spins up minus the number of spins down over the total number of spins, it's the magnetization per spin, what happens is below certain TC, this comes up like this, or it could equally well have come down like that. And the thing that makes this interesting is how the asymptotics of M as I go towards TC. Now, if I said to you, okay, I'm giving you 10 seconds, you have to come up for a theory for what the shape of this curve is. Okay, so what you would say is, oh, that's easy. What you'd say is, let's draw T as a function of M. It's a curve that looks like this. It has to be symmetric, because I've got up-down symmetry in my original Hamiltonian. So it's a curve that looks like this. I can expand this function in the Taylor series about this point. So I can say that T is equal to TC minus some coefficient times M squared, blah, blah, blah. And so therefore I get that M is going to behave like TC minus T, the 1/2 pound. There you are, 10-second theory for this, and you have to do far more work than that 10-second theory to do better. What? It's the fastest derivation of Landau theory in the universe. I totally agree. Okay, so it's fast, but it's wrong. So the actual behavior is M goes as T minus TC over TC, the variable that I called little t, to a power beta. And for at least for an Ising magnet, beta is about 0.326 something or other. Okay, so that's the first stylized fact. Second stylized fact, is my chalk. Second stylized fact is if I draw the phase diagram, so here is H, here is the external field, then what happens is this. There's a point TC, and below that there is a cut or a discontinuity. Why is that? Well, when I'm below TC, the magnetization is non-zero. Obviously, M is non-zero. Right? So what's happening is over here, when I get to near zero temperature, all the spins are pointing up mostly. Maybe one or two are pointing down. If I go on the other side, they're all pointing down, maybe one is pointing up, and so on like this. So that means that across this line here, there is a discontinuity. Here the magnetization is less than zero, here the magnetization is positive. So that means as a function of external magnetic field, I point the spins up and I point the spins down, there's a discontinuity here. So that means that M has a discontinuity. And because M is M is the derivative of the free energy with respect to h. That means I have a first order phase transition in this direction. So that's a first order transition. Now in this direction, as I go down in t for h is equal to 0, what happens is the magnetization goes up like this, and it goes up in a continuous way. So this is a second order phase transition or continuous phase transition. Now, what happens at the critical point? So here is the critical point, right here at h equals 0, t equals tc. And then the second stylized fact concerns linear response theory. So if I tell you I apply an external magnetic field to a magnet, how much magnetization does it induce? Your 5-second theory for that is linear response theory. The magnetization that is induced is proportional to the external field that I apply. That law is called Fourier's law. That's what you would normally expect. It's not true at the critical point. At the critical point, what happens is m scales as h to the power 1 over delta t equals tc. So linear response theory breaks down at the critical point. Now, what Widom and Kadanoff realized in the about the same time independently. The history books say Widom discovered it first, but I know from talking with Kadanoff and so on, but in fact this was already understood by him as well. So let's call it Widom scaling, but really it was known to Leo and he based his famous 1966 paper on this. So what Widom discovered and Kadanoff built on was this. I can explain both of those stylized facts if it turns out that the stylized facts come from a similarity assumption. And that similarity assumption is m as a function of t and h goes like t to the beta times some scaling function of h over t to some exponent delta. And I wrote down over here little h is h over kbt and little t is t minus tc over tc. Those are my small variables. So now the question you should be asking is, okay, well, this is interesting if it's true, because like all similarity solutions of differential equations, it says I've got a function of two variables, but it's really just a function of one variable, which is this. So the question we want to ask is, how does this explain this? So let me just let me show you why it's true, and then how one can test it. So what it means is, so let's suppose it's true. Then what it means is that if I take data for T1, T2, T3, a whole range of temperatures, reduced temperatures, and H1, H2, H3, and so on, the magnetization will in general fill the plane. It will be a function of both T and H if I plot them as a function of T and H. So what I do though instead is I plot H over T to this exponent delta and M as a function of T and H over T to the beta. And then what will happen is all my data, if this statement is true, will collapse onto a universal curve like so. So here is the curve. I'm going to draw through it. And these blobs are meant to be different data points. And this is a universal data collapse. Now, let's see how do we go from here to here. So what you have to argue is the following. The only way this can happen is, first of all, if we want this stylized fact to be true, that in zero external field, m goes like t to the beta, what that tells you is that the function f of z must be a constant when z is equal to 0. Okay, so no external field, h is equal to 0, then we just get this t to the beta, so that's what we want. What happens for large z? So if I take the argument of this function, this is the thing I'm calling z. If I take this function, I say large z means h is non-zero and t is going to 0. So now we're getting to the large z asymptotics. What I need to do is, as I send t to 0, but h is non-zero, I need to recover this. And you can see here that here's n and here's h, and little t is nowhere to be found. So the only way that can happen, just as in Kolmogorov's argument, is that as I take t goes to 0, t must cancel out. To get stylized fact number 2. And the only way that can happen is if the scaling function, since z is proportional to h, the only way that can happen is that we need that f of z scales like z to the power 1 over little delta, and z goes to infinity. And then the t dependence cancels out, but wait, it can't cancel out because I've got this unknown exponent over here. So the only way that it can cancel out is if delta is equal to beta times little delta. And so this delta is not a new exponent at all. Delta is equal to beta delta over here. And so what it says that when I'm plotting this curve here, what I'm actually plotting is t versus beta over delta. So that is the scaling argument. And let's see if it works. So here are the data. So you can see over here, here is temperature scaled in a particular way, magnetization scaled in the way that we talked about, slightly different. These are data from 5 different magnetic materials. They're not the same material. And because these exponents are believed and are shown in RG theory to be universal, meaning independent of the coupling constant, independent of the exchange interactions between spins and so on and so forth, independent of the parameters in the Landau theory, all the data collapse into one universal curve. And this solid line that goes through here is the renormalization group prediction with no adjustable parameters. It goes right through the data. Okay, so this is fantastic. Because here we've got a model, like the Ising model, the Landau theory model. And this model gives precise prediction in agreement with experiment, the critical exponent, data collapse, so on and so forth. But this isn't really true. This is a model of a model of a model of a model of a model. Okay, why? We started off with quantum chemistry, and we went to electronic structure, quantum Ising or Heisenberg model, throw away quantum mechanics, classical Heisenberg model, then make a Taylor expansion of the thermodynamics. We get Landau theory. Each step here is completely unjustified. There is no small parameter that allows you to do this. Every expansion that you're doing here is a non-systematic approximation, which would make an applied mathematician tear their hair out. But yet, how is it possible that even though you make all these approximations, you're still able to get a precise prediction? Okay, and that's the question that renormalization group theory answers for you. It shows you, like the answer I gave to somebody else's question back there, that all these other terms turn out to be irrelevant. They don't change the asymptotic behavior. And that's the statement of universality. Okay, so I'm not going to give you a lecture course on how this works. It's a huge surprise that it happens like this. And when you think about it, this is why physics works at all. Okay, let's suppose you're a material scientist or a chemist or a fluid mechanician. When was the last time that you needed to worry about the radiative corrections to the mass of the top quark? You never did, right? You neglected all of that physics without any justification. Okay, it works for the same reason as this. That's why renormalization group is so important. It gave us a way to reconceptualize how physics works. Static theory. We have Navier-Stokes equations, which is coarse-grained, like the Ising model. Then we have the question I want to ask is, in the context of the turbulence transition, what is the, oh my goodness, what is the Landau theory and what is the renormalization group universality class? Okay, how long do I have? 15 minutes. 15 minutes, okay. Well, we won't get to all of it. All right. When you have a phase transition, everything works because right near here, you have weak, long wavelength modes that control the singularities, the non-singular, the non-analytic behavior, which is what a phase transition is. So in all phase transitions, the modes that control it have to be weak. They're going to zero, but they're going to zero in a non-analytic way, and that non-analyticity contaminates all of the statistical thermodynamics. So what we're going to do is say, look, if we're going to look for that, if that's going to happen in the laminar turbulence transition, we need to look for weak, long wavelength collective modes that control the dynamics. So what we did was we did the DNS of 3D Navier-Stokes using Ashley Willis's open pipe flow code. There's some details here, but don't worry about it. What we found was this. When you look at the, we did the simulations, looked at the data, hunted around, eventually we discovered this. If you look at a single puff in a pipe, a flow domain which is 10 or 20 pipe diameters long, big enough to contain a puff, we just look at the dynamics of that puff. What we see is that you get small scale turbulence, and then there is an emergent mode, which we call a zonal flow, because it is Z independent along the flow like that. It's an azimuthal flow. It is time dependent and it has radial structure, as shown over here. Now, the important thing is that the energy of that mode oscillates in time. And it oscillates out of phase with the energy of the turbulence. So the turbulence and this emergent large-scale zonal flow mode, which is weak, are oscillating 90 degrees out of phase. And so what's happening here is the following. The turbulence is the anisotropy in the Reynolds stress is creating flow that is then non-isotropic and flows out to the boundaries and hits the walls and starts to go around one way or another. So that anisotropy, due to the Reynolds stress, creates this zonal flow. That zonal flow then shears, and by shearing isotropizes, and therefore suppresses the Reynolds stress, the turbulence. So then the turbulence has now been suppressed, but the turbulence was the source of the zonal flow in the first place. So now what's going to happen is the zonal flow itself is going to go down, and because that's gone down, it's no longer restricting the turbulence intensity can then rise up again. And so what you have is this feedback loop, and this feedback loop is what happens in the predator-prey ecosystem or any activator-inhibitor system. So in an ecosystem, what happens is you have prey this sheep over here, and the sheep is being preyed upon by this predator. So here is a wolf. I'm a biophysicist, so everything is a spherical cow as far as I'm concerned. Right? So what's happening is the wolf eats the sheep population goes down. Now the wolf hasn't got enough food to eat, so the wolf population goes down. Now there isn't too many predators around, so the sheep population goes up. And now there's lots of food, so the wolf population goes up. And you have these population cycles. That's what happens in the predator-prey ecosystem. The analog of that here is what I told you about the relationship between the turbulence and the zonal flow. Okay, so I'm going to seriously overrun because because I'm an idiot. So I think what I will do is I'm going to skip this, but if anybody wants to talk about predator-prey dynamics, I'll be happy to talk about it later this afternoon. I already know there were some people who wanted to talk about population dynamics. Okay, so let's skip ahead. So the way that we describe this is we are forced to describe this by stochastic processes. Okay, I have a quick question here. Here is the energy. So you can see the scale here from this. It's small in terms of energy, but it should be small. Okay. The question is not how big it is. The question is a mode can be small, but if it contributes 100% to the non-analyticities, that's the thing that's important as a phase transition. So if I look at the magnetization in a magnet, I look at the heat capacity associated with those modes compared to the overall heat capacity of a magnet, it's infinitesimal. But all of this thing that contributes to the non-analytic behavior, which is what we're interested in, comes from that mode. Did I answer your question? Yep. So if you write down differential equations, the Lotka-Volterra equations, and I'll be happy to go through these afterwards in blackboard or discussion or whatever. Those equations, which I'm not writing down now, if you solve them deterministically, do not give you population cycles. In order to be able to explain why you get population cycles in ecology using the equations that ecologists give you, they do not give you population cycles. They give you fixed points. And you can see that shown over here. And what's actually happening is you are getting a stable fixed point, which has a spiraling, when you look at the linear stability analysis, it is stable, but it has an imaginary part. So the eigenvalues, the stability eigenvalues are complex. And so what happens is you get decaying modes that are excited by random fluctuations that then spiral into the fixed points. And so when you do this, when you write down a stochastic theory for this, you get these persistent noisy oscillations like this. Now, how do you write down the stochastic theory? Well, A is the predator, B is the prey. And what happens here is that these things are floating around in an ecosystem. When the predator runs into a prey, with some probability P, it eats it, uses the energy that it gets from that to make a baby predator. And so you get A plus A from A plus B. Similarly, the prey eat the food, and then they get enough energy to make babies, and so you get B plus B. And then the prey actually compete for the food that they eat, the resource, and so that's controlled by this reaction here. Two sheep duke it out, and one wins and eats all the food, and the other one doesn't. And so these are the reactions that describe a ecosystem. If you take these equations and write down the stochastic theory of that, so that's now a stochastic PDE or stochastic ODE, the mean field theory of that gives you the classical textbook solutions that you see here that don't describe this. When you go to the 1/n fluctuations, meaning you start doing an expansion in the system size, the lowest order fluctuations about mean field theory give you these stochastic solutions here. And that's the mathematics that we use in our work. Okay, I've walked you through this. These are the equations. Let me walk you through these, and I'm going to, if I go over one, I'm going to just go into next lecture. So the prey grow by eating food, so they have exponential growth. There's a limited food resource, so there's a carrying capacity, which is given by K. Then the predator hunts the prey, and the predation probability is proportional to the prey and predator densities, so you get this term PUV. And then the predator, noted by V here, is born at a rate given by how many prey it has, and then it can also die off. And those are the solutions that I showed you go to fixed points and not to what you want. So the stochastic theory is every term in the stochastic theory here represents what happens in the ordinary differential equation. And when you run that, you get these noisy population cycles. And again, what's happening is the noise is kicking you away as you spiral into the trajectory and then getting kicked out and so on. And so you've got this damped motion into the fixed point being kicked out, and the complex eigenvalues cause you to circle the fixed point. And the mean field theory, the Lotka-Volterra equations, they over average, and so you end up with they remove this phase structure of the population fluctuations by averaging, and so you get nothing. Okay, I'm going to skip this. Okay, now I want to talk about turbulence again. So give me 5 minutes warning, Peter. Okay, 5 minutes. Okay. All right. All right. I can take the Navier-Stokes equations, and I can expand them as a field theory, as was first done by Bill Wilder at University of Illinois. And what you do is you simply say, here is my mean flow. So in this case, the laminar flow. Here is the turbulence. I write down the velocity field as a decomposition into those two things, plug into Navier-Stokes equations. Navier-Stokes equations have a quadratic nonlinearity. So that means that every possible term in perturbation theory has a triple vertex like this. If I'm trying to find a Landau theory for a non-equilibrium phase transition, the rule is this: write down every possible term that can be allowed by symmetry. It's not disallowed by symmetry. That will have to be there. So let's write down the lowest order interactions, vertex interactions, that I could have if I expand the Navier-Stokes equations like this. Here they all are. And if I look at these, and remember that A is the predator and B is the prey, there's a kind of wave-particle duality. Every possible diagram here corresponds to every predator-prey interaction that I'm showing you here on the left. So here, for example, zonal flow and turbulence meet, something happens, and turbulence dies, and you get more zonal flow. That is the reaction A plus B goes to A plus A. So there's this map. Okay, so now you have a very simple question. If I take a stochastic predator-prey ecosystem, which never knew anything about the Navier-Stokes equations, what we should see, if this works, is we should be able to recapitulate the statistics that I showed you for the metastable puffs and spatial temporal intermittency. So in the predator-prey model, what you do is you set this up in space. You start off with an initial population of predator and prey. It turns out that they die away and you get a metastable state. If you increase the birth rate, so you can have coexistence of predator and prey, the population split into two like this. So you have the complete analog of this phase diagram. Here are the pictures. This is in pipe turbulence. This is turbulence intensity as a function of space and time, showing the puff moving backwards. Somebody asked about this in the lab frame, slightly moving backwards and then splitting. Here we have the same thing in the predator-prey ecosystem, doing the same thing like that. If we measure the statistics of the extinction time and the time between population splitting events, this is what you get. This stochastic predator-prey model is the Landau theory for the laminar turbulence transition. And you see it recapitulates the super exponential behavior that I told you about last time. So the extinction in this ecosystem, if you will, is the death of turbulence as you go down in Reynolds number. Okay, so I'm going to leave this to next time. So next time, I apologize for taking so long. I had a lot of questions. I wanted to explain some things to you, so we'll still get to everything. Next time, what I'm going to talk about is how do we answer the question of what is, if this is a phase transition, what's going on here, what is the universality class of that. And I'm going to show you next time that it is directed percolation. I'm going to show you that if I take the stochastic predator-prey ecosystem, I can map it using stat mech techniques and field theory techniques that you don't need to know into a field theory that first came out in the high energy hadron scattering called Region field theory, a non-Hermitian field theory. And that field theory is in the universality class of directed percolation. Now, if you don't know any of that stuff, it doesn't matter, because I'm going to explain it to you graphically in a simple way, just like my instant derivation of the Landau theory on the blackboard. So I will show you picturesquely, even if you don't know anything about stat mech or field theory, why this happens. Okay, so you'll understand why this is directed percolation.
This will be right.
Say it again.
This will be right. Or is that one
Well, no, this one will be right because it will actually map it onto directed percolation, but it won't tell you what the exponents of directed percolation are. And then to get the exponents of directed percolation, you go and thumb through the literature, because 20 years ago, everybody worked it all out in gory detail. So the analogy, so if I did that one, the analogy between, say, magnet and liquid gas and so on, I can do that based on symmetry. I can't calculate the exponents correctly. Here I'm going to show you why it's in the universality class of it, but then to get the exponents, I use the literature. Okay, so I'm going to stop there for today. And next time I will carry this on and then talk about the third topic. And if anybody wants to have a discussion about the population dynamics of predator-prey systems, I'm happy to do that afterwards, either in the afternoon or whatever people want to do. So just message me. And I will put those things will be in my notes anyway. Okay, thank you.
Yeah, 2 minutes, but so I just wanted to ask, so previous lectures, this topic of RG and turbulence came up, and they made statements like RG fails for turbulence.
Yes.
Here, it seems like RG works for turbulence. I guess if you could comment on.
So the question is, some people say the normalization group doesn't work for turbulence, and I'm saying it does. So what's the difference? So the difference is this. First of all, I'm talking about the transition to turbulence at Reynolds numbers around 2000. When people are saying the normalization group doesn't work for turbulence, what they're talking about is how do you explain the Kolmogorov scaling at high and multifactorial scaling at high Reynolds numbers. And so it's in a different regime, and it's a completely different physics. Okay, so that's point number one. Point number two, it's not true that the renormalization group doesn't work for turbulence. It just means that we don't know how to do it. The first attempts that were done to try that, Yakot and Orsag would be one of the examples, was technically not correct. Okay. There's plenty of problems where we know renormalization group should provide a description, but we simply don't know how to construct the renormalization group transformations and do the calculations. That is what I would say is the situation with the fully developed turbulence. In any case, in fully developed turbulence, there's many more interesting questions, which certainly have a renormalization group component. And I'm not going to lecture on that, but the buzzword for that is spontaneous stochasticity. And I don't know if Freddie Boucher maybe mentioned it. I'm not sure, but that's active work that our collaboration on turbulence is studying and trying to develop a renormalization group of spontaneous stochasticity. And if you want, ask me questions in Slack, and I can put some of the recent papers on that there. Okay. So did I answer your question? Most important thing is I'm talking about the phase transition to turbulence, not fully developed turbulence. Okay, next question. The construction of the theory is not necessarily based on symmetry. I mean, so you mean like up-down symmetry, like in a magnet, for example? Oh, every term that is not forbidden by some symmetry is allowed. There isn't a particular symmetry that I can point to that's, well, it has to have 3 vertices. So you have to write down all the lowest order interactions that have 3 vertices and then draw those. And then what happens is you look at the lowest order fixed points that you get from those, and then you ask to see if terms of higher order, if they would be relevant and would change the predictions of the terms that you've kept. And that's how you have to do it. So that's what was done. Do you know, have you heard of the KPZ equation? No, okay. So that's an equation that describes interface growth. And again, this technique was used to write down the generic behavior of dynamics of interfaces. So really the point is we're trying to do a low order expansion in terms, then look at the terms, the lowest order terms, and ask, are any of the higher order terms, do they change the behavior of the low order terms that we keep? And that's a complicated process to do, and I'm not going to explain that. Okay. Did I answer your question?
Maybe one more question. Professor, I'm wondering how the universal structure you shared turbulence transition, shear transitional turbulence, or is only Hagen fluid flow?
So the question is what happens in a shear flow specific to just the pipe flow, or is it more general? So that's a great question. So I'll talk about this next time, but let me give you the preview of the answer. So maybe a few months ago, I would say we don't even know this really for pipe flow. It's predicted, but we can't really prove in pipe flow that is actually directed percolation. So the work that we've done, which is unpublished yet, we're just about to submit the paper. It's written. We've taken pipe flow measurements and actually shown that it really is in directed percolation universality class. It's hard to do the experiments in a pipe because a pipe is finite, and you'd need a pipe that goes from here to the moon or something like that in order to be able to do the experiment to nail it down. So the experiments I'm going to show you next time are done on a closed flow, a Taylor-Couette flow, and there we can show experimentally that it is directed percolation, and now that's been done in both closed flows in 1 and 2 dimensions. And that was in Bjorn Hoff's work in Physrev Letters just a couple of months ago. So we have then other simulation evidence from Chantry and Tuckerman and Barclay on a shear flow in 2D or Willef flow. And there we also know the evidence isn't quite as good, but we know there also in that flow, you get directed percolation. So I would say we don't yet know the full generality of this to all flows to be able to make a categorical statement. If you look in the literature, there is nothing in the literature to show you that in a pipe flow, you really got compelling evidence that it actually is directed percolation, as we predict. But I'm telling you that we do, and I'll show you, if I have time, some of the data for that.